This is Physical Science 1, Chapter 4, Part 3 on the laws of motion. In this portion of the video lecture, we will be discussing Newton's third law of motion. Newton's third law of motion states that when one object exerts a force on a second object, the second one will exert a force on the first that is equal in strength and opposite in direction. A lot of times Newton's third law is called action and reaction forces. So as the balloon here is, the air is being let out of the balloon, so the air rushes down, and that action causes the reaction of the balloon to go upward. So when a force is applied in nature, a reaction force occurs at the same time. So again, if you're on the skateboard, you are pushing with your foot as an action, and the reaction is that you travel in a particular direction. Same thing with rowing a boat. When you row in one direction, that is going to cause the boat to go in the other direction. So they're opposite and equal forces. Now this may seem weird that Newton's third law would state for every action there's an opposite and equal reaction, because if that happens, it would seem as though everything would cancel out and nothing would move ever. But even though the forces are equal, they're not balanced because they act on different objects. So, for example, a swimmer. The swimmer acts on the water, and the reaction of the water pushes the swimmer forward. So a net force or unbalanced force acts on the swimmer, so their change in motion occurs. So they swim forward or backward, depending on whichever direction they want to swim. So even though it would seem as though action and reaction forces would always cancel out, those forces are applied on different objects, so motion can still occur. When we talk about Newton's third law, we need to introduce the concept of momentum. Momentum is a product of mass and velocity. Momentum we use as a symbol as a lowercase p. Remember, because a lowercase m means meters. So we use p to symbolize momentum. So we take the mass of an object times its velocity, and that's our momentum. So the unit for momentum is a kilogram times meters per second. So when we take a look at momentum and acceleration and force, we can kind of revise Newton's second law equation. Remember, we talked about Newton's second law is the force is equal to the mass times the acceleration. We can take a look at initial and final momentums and divide that by a time also to get a force. Now, momentum of an object does not change unless its mass, velocity, or both of those things change. So momentum is always going to be conserved. If you've ever seen the little toy, the Newton's cradle, when you pull one of those steel ball bearings back and clack it in row, the momentum transfers through all of the steel ball bearings to the very end one, which kicks it out. So momentum can be transferred from one object to another. So like billiard balls or a pool. So if you hit the cue ball into the yellow ball, the momentum from the cue ball will transfer to the yellow ball to go, hopefully, into the pocket. So the law of conservation of momentum states that if a group of objects exerts forces only on each other, then their total momentum does not change. So we have our little train cars here. So before, they were each traveling a particular velocity, and they each had a particular mass. Once they attach and move, then all of those forces are combined. So the total momentum does not change. So the results of collisions between two objects is going to depend on the momentum of each object. So collisions will depend on both the mass of that object and the velocity at which it was traveling at. So when an object hits another from behind, momentum occurs in the same direction. So the air hockey table. If you have the puck, you hit it with your paddle, and the puck goes across the table because you're hitting it with that momentum and it's transferring to the puck to go across the table in the same direction that you were hitting the puck. When an object hits another head-on with the same force, then the momentum is going to be zero. So if the forces are equal, then ideally, if we had two air hockey pucks hitting each other with the exact same force, they would stop where they hit. If one object, however, hits another head-on with more or less force, then that momentum will be transferred in the direction of whichever force is greater. So if one object hits another head-on to the right with more force to the right, then that puck will travel to the right. If it hits it with more force to the left, the puck, that momentum will transfer and motion will occur into the left. This has been Physical Science 1, Chapter 4, Part 3 on laws of motion.